Atomic structure is an amazing thing. But before we get really into it and deal with how tiny atoms truly are, let's kind of get a foundation for what we're talking about here. You'll recall in Bugs Bunny cartoons that you probably saw something that looks like this for an atom, where you got this thing in the middle, and then you've got three circles that are kind of drawn like this. That's a terrible drawing. Don't judge me. This is the old school view of what an atom is. And I'm going to kind of walk you through as to how that came to be and what our current modern atomic structure is viewed to be. This all begins with chemistry. Chemistry is an experimental science that uses scientific method to design theories. Theories are continually modified as experiments get better and as observations can be made. But these observations must be careful, and we must kind of figure out trends which become laws, and then these laws, once they stand the test of time, become theories. And so a lot of what we're going to be talking about with regard to atomic structure is really kind of atomic theory. So, atoms are the simplest part of matter with the same properties. Democritus, back in the 400s BC, basically came up with this. He said, atoms are a thing that cannot be divided. So, A is not, and Tom has something to do with a thing that, or a division. You cannot cut an atom. That's what he said. Now, since then, we have shown that this is not true with something called nuclear fission. But at the time of Democritus, it was a very sound theory. Now, matter is something that occupies space and has mass. So we can look at, say, fire. It looks like it occupies space, but it has no mass. Okay? So fire is not matter. I am matter. I matter. So do you. Matter is made up of atoms, and if all atoms are alike, then we can say that that's an element. But not all atoms are alike. They are very different. And in fact, these different elements, when you start to be putting them together, can really do some amazing things. So we can look at nitrogen in the air. Nitrogen is an element. Nitrogen is in the form of N2. That's the abbreviation for nitrogen, is the letter N. 2 right here basically says you have two nitrogens that are stuck together. Oxygen looks like O2. You have two oxygens that stuck together. Pencil leads, also known as graphite, at least the old school, if you're an artist, you understand graphite pencils. That's just C, carbon. So elements can be kind of stuck together in a couple of different diatoms, as it is. This is diatomic. Or you can have elements that are by themselves. But it's just that particular atom. They are stuck to one another. Now, there is a diatomic 7 that I like to think of, and that is nitrogen, oxygen, fluorine, chlorine, bromine, iodine, that's 6, and way over on the other side of the periodic table is hydrogen. Those things all show up as diatomic kind of things. Each one of those things is a 2. You have two things in the middle. you have phosphorus and you have sulfur. Those are different. Phosphorus is P4, sulfur is S8. Everything else on the periodic chart, which we'll get to in a second, is just the simple elemental form of C or CO or AL or TC. It doesn't really matter. But when we start looking at this periodic chart, which we're going to get to very shortly, now then, we can start to see that we have this periodic trend of the diatomic 7 with a couple of exceptions there. Now, that said, when you start to combine different compounds with one another, you get something different. So, in this case, compounds are going to have more than one element, but they're always going to have the same types, same ratios of elements with them. So, for instance, water is always 2 hydrogens and 1 oxygen. Water always is H2O. H3O is not water. Carbon dioxide is a carbon di as in 2 oxygens. That's carbon dioxide. Always going to be carbon dioxide of CO2. Now, if it becomes CO, that's a different compound. That is carbon monoxide and is distinctly toxic to us. CO2 is toxic to us, but carbon monoxide will kill you a lot faster than CO2. So that becomes a thing. So now then we have 2 different compounds, right? Both made from carbon, both made from oxygen, but in different proportions. Compounds with different atomic ratios are always going to be nice and predictable. That predictability is why chemistry becomes a science. It's reliable, it's predictable, it's logical, but you got to know the rules. The rules for baseball are reliable, predictable, and logical. But if you don't know them, who knows? Tennis is the same way. That's why with tennis, there was a distinct bias against poor people in England. So they wanted to get rid of the reliability. So in tennis, you score via 0. Your first point scored is 15. Your second point scored is 30. Your next point scored is not 45, it's 40. And then you go up to 41. Oi! So they did this so that poor people couldn't follow the game. It's not fair if it's not reliable. Chemistry is reliable, but you got to know the rules. If you know the rules for scoring in tennis, then tennis becomes a game that's easily played. But you got to know the rules, and that's what we're going to be talking about here. Mixtures are when you have things that mix together, but they're not compounds. Okay? So, water is a compound, H2O. This is water. Salt is a compound. Salt is NaCl, sodium chloride. We can take salt and put it in water. And whenever we take the salt and we put it in water, then we get, hold on, you ready for this? Salt water. But we can take the water and evaporate it off, and it leaves us with a big pile of salt, which you see in the actual salt flats of Nevada. So you can have this mixture. And whenever you look at all sorts of things, if you go out to the Dead Sea, you got a lot of salt, right? If you go to the Great Lakes, you don't have near as much salt. So mixtures are a ratio This is a ratio of two or more compounds. COMLBS. LBS is pounds, right? Two or more compounds, but it's a variable ratio of two or more compounds. A compound has a unique ratio of atoms. So this becomes something that's really, really important to make sure that you understand. Solutions, these are just liquid mixtures. That's all they are. Liquid. Let me not say liquid mixtures. They are actually fluid mixtures. And these fluid mixtures could be in air or in water, for instance. So air is a solution. Air, as a solution, has nitrogen, it has oxygen, it has argon, it has CO2, and they are all in different ratios. See how they're a mixture there? We also can have aqueous mixtures. So this is an air. We can have an aqueous mixture. And an aqueous mixture means it's in water. So, for instance, when you look at blood is an aqueous mixture, right? You have H2O, you have cells, you got a little bit of O2, you've got lots and lots of different things. You got micro and macronutrients, you got electrolytes, you got lots of different things. So another mixture that you can have is mud. Mud's a mixture, but you know what else is a mixture? How about beaches? If you look at beaches, you have a bunch of sand, right? And all this sand, if you look at the beaches that I grew up on, all the sand, you got little chunks of oil, you got some rocks, you got some seaweed, you got all sorts of different things. If you look at it and you go to digging in these beaches to get a nice sandcastle built, what happens is you have all sorts of different things. You got some rocks, you've got some sand, you've got some oil, you've got some lots of other things. But whenever we're looking at these things, what we find is you have different kinds of mixtures. So when we're looking at this, these beaches are something called heterogeneous mixtures, because the rocks and sand and oil aren't mixed up to where you can't tell them apart. You can separate them out. You can pick it apart that way. But if you look at mud, for instance, like a good silt mud from the Mississippi River, what you find is it's homogeneous, isn't it? You can't just pull out the mud, the dirt. You have to do something different. Mud feels like it's a homogeneous mixture, but in reality, it's actually heterogeneous, right? It's heterogeneous because we can filter it. Because it's filterable, it's a heterogeneous mixture. Milk, we can put it through the same funnel or same filter as mud. Mud will filter, milk won't. Milk becomes this thing right here. Milk becomes a homogeneous mixture. It is a solution. Air is a solution. You can't tell nitrogen from oxygen, but you know it's there. Same with fresh blood. Now, other examples of mixtures. Embalming fluid is a great example of a mixture. Now, I would hope that our embalming fluid would be homogeneous, right? You don't want floaties in the embalming fluid. It could stop up the capillaries and you don't get good flow throughout the entire body. We've got to make sure that it's a homogeneous solution. Now, I mentioned atomic theory a little bit ago. And yes, atomic theory goes all the way back to Democritus. But the first observations of atomic theory come with a French man named Lavoisier. He is known as the father of chemistry. And he carefully observed all sorts of things to where he realized that the law of conservation of mass or matter is a thing that says if I start with X number of grams and I react it with something that has Y number of grams, if I react those two things together and I get a new thing, whenever I weigh that new thing, X plus Y, this new thing is going to weigh X plus Y grams. You don't have matter or mass that can be created or destroyed. And he also came up with, there's this law of constant composition. That's what I was just talking through that says H2O is always H2O. HO ain't H2O. It's something different. We'll talk through that and what that means. Now, there's a couple of other things that we got to pay attention to. One of those deals with something called properties. Properties are stuff that you can observe. A physical property you can observe without changes in the chemical composition. So when we take water and we put it inside of our pot so that we can boil our noodles for our lunch, as we apply the heat, some of that water becomes gas, right? And that gas we call steam. So we have water down here that becomes steam. But the steam is still the same H2O as water. That is this thing called a phase change is in fact a beautiful thing called a physical property. And there's lots of different kinds of phase changes. So you have melting, where you go from a solid goes to a liquid. I'm putting L there for liquid. You can have freezing, which is backwards, right? Freezing is where you'd have a liquid that goes to a solid. You can have evaporation, which is where you take a liquid and you make it into a gas. You can have condensation, where you can take a gas and turn it into a liquid. And then there's this weird thing that you can do, where you can take a solid and turn it into a gas. You ever wonder what happens to snow when it's freezing outside and yet the snow's going away? It's not melting. It's doing something called subliming. This is called sublimation, where you have a gas formed out of a solid. And if you go from a gas directly to a solid, then what you have is something called deposition. That's a lawyer's favorite phase change, by the way. Save your laughter. It gets worse. So, these physical changes are a big deal. But chemical changes are more interesting from a chemist's perspective. Chemical changes happen, these chemical properties happen when you observe a change and it changes the chemical composition. So, for instance, cremation is a combustion reaction. It is a chemical change of a body into ash. So you take a body plus O2 and you add something called heat. So I'm going to put heat there as a triangle. That's an old school way of saying this. And then you get ash. And then that's what cremation is. Decomposition is another type of chemical reaction. Preservation is another type of chemical reaction. You change the chemical composition. You cannot go from ash back to a body. That's very difficult to do, at least by humans. Now, this law of constant composition, as I've said, is basically saying your compound is always going to be the same compound. These ratios will not ever change. Glucose, for instance. Glucose is C6H12O6. That's glucose. Formaldehyde is always CH2O. Always. So these are distinctly different. Notice that glucose has carbon, hydrogen, and oxygen. Formaldehyde has carbon, hydrogen, and oxygen. It looks like they're in the same ratio if you can divide things out, but they're not, which is a fascinating thing. Formaldehyde looks like this, where you have a carbon double bonded to an oxygen, single bonded to an H, single bonded to another H. Glucose is in a hexagonal form. You've got to have 6 of these things. So if you're going to do 6 of them, you can draw it as a hexagon, and then you put everything else around it. Is this different than this? Yes, it is. So even though you may have the same ratios, same reduced ratios, those are different compounds altogether. All right, so John Dalton came up with an atomic theory. In his atomic theory, he basically said each element is composed of atoms, which can neither be created nor destroyed. Yes, I'm good with that. He says all atoms of an element have the same mass and same other properties. I'm good with that too, which basically says an oxygen in the presence of a fuel is always going to burn. That's that chemical property of oxygen. He also said that atoms are going to combine in simple whole number ratios to form compounds. That's that exact number, like that mathematical tool thing that I talked about earlier last week with regard to Roger Maris hitting 61 home runs in 1961. You're never going to have half a hydrogen. It's always going to be 1 or 2 or 3 or 4 whole number ratios to form these compounds. So, after that, we had to figure out, how did they do it? So, Ernest Rutherford came up with this gold foil experiment. In this gold foil experiment, he shot a radioactive particle at gold foil. The radioactive particle that he shot was actually an alpha particle. That's an alpha, by the way. An alpha particle is a pretty big particle. It's actually just a helium that has, and I'm going to put this here, it doesn't mean anything to you right now. It's a helium atom, a helium nucleus. So most of those alpha particles went straight through the gold foil, which is like single atom thickness. Single atom thickness. Most of those nuclei, those those radioactive particles flew straight through. So he concluded that most of the atom was empty space. What was left was something called a nucleus. So basically, he said, you got a nucleus here, and then you got something all empty space. Empty space. Okay? Not Middle Tennessee space, but you get the gist. How did that look? It looked like this. Well, yeah, I'm going to skip this one. Never mind. Here's Rutherford's gold foil experiment. He shot those alpha particles through. These are relatively undeflected, and you had some that backed up. And you could see them and how it plays out in this little circle of photo paper, basically. So, the atom is mostly empty space. Basically, he said, you got this little bitty nucleus here, most everything's going to go through. So, we know we got an atom that has a nucleus, and that nucleus is mostly empty space. Well, another person came back and said, there's this neat little thing called a cathode ray tube. You saw that on the old-timey TVs like what I grew up with. And it had negatively charged particles that would be shot somewhere, and it would make a picture. Well, atoms are neutral, is what we know now. And so with these cathode ray tubes, basically, what you found is that we can move the electrical charge interestingly. So if I have a positive anode and a negative, if I have just a regular cathode ray tube, it's going to go straight from, let me go ahead and change color to this thing. It's going to go all the way to the end is what's going to happen. But if I put something that's positively charged up here and negatively charged here, that cathode ray gets deflected toward the positive, which means the cathode ray now, the cathode ray is negatively charged. And what happened was, because we could do this experiment, we determined that we had something called these negatively charged things, we're going to call them electrons. And these electrons, remember, we got a nucleus here with all my empty space. It ain't empty. We have electrons, which I'm going to call E minus. We have electrons in this empty space. But these electrons are all constantly moving. They're moving from here to there to yon. So, we also, if atoms are actually something called neutral, we know that atoms are neutral if we have one electron, right? Which is negatively charged. See the negative right there? That means we'd have to have one proton. And a proton is positively charged. And what we find is when you have one electron and one proton, then you have a hydrogen atom. And then a little bit later, a lot later actually, in the 1930s, they found that there's something called a neutron as well. A neutron walks into a bar, asks the bartender for a drink. Bartender gives him the drink. Neutron says, "How much do I owe you?" Bartender says, "For you, no charge." because neutrons, by name, neutrons have no charge, hence the 0 there. And so now then what we can do is we can start to see a combination of protons, neutrons, and electrons. In the nucleus contains protons and neutrons. The electrons are all over the place elsewhere. Remember that little orbital kind of thing that I said, where you have a nucleus here and you got these things? Those orbits, Niels Bohr came back and said, those are electrons. Since then, we found out that orbits aren't something that electrons wander through. Now, atoms of different elements have different kinds of things. So a hydrogen has 1 proton, a helium has 2 protons, and it has 2 neutrons. So we can label this in all sorts of ways. So a hydrogen has an H. Well, let me do it this way. Hydrogen is H in terms of its actual abbreviation. It has 1, so we label it like this. This here is the number of protons. This here is the number of protons plus the number of neutrons. So when we label hydrogen, we say hydrogen has a superscripted 1 and a subscripted 1. So that gives you the number of protons, number of neutrons, all that other good stuff. Helium, on the other hand, He, has 2 protons, so we put the 2 in the bottom. And the protons plus neutrons gives you 2 plus 2, which is 4. So now then we get helium that looks like this. Carbon has 6 protons and usually 6 neutrons. So carbon would look like this, where you have a carbon here, 6 protons, and then 6 plus 6 gives you 12. These things are pretty important. Now I want to point out this thing. Carbon usually has 6 neutrons. You can have a carbon that has 7, but it's going to have always 6 protons. So these things here, these are something called isotopes. Just like I weigh differently than another man, because I might have more or less neutrons, if you will. See that as fat, weight, whatever you want to call it. Carbon, though it can be still a carbon, can have a different weight as well, a different mass as well. That's a very interesting thing. Atomic number is defined as the number of protons. That's what your atomic number is. So when you go and you look up something on the periodic table, which we'll talk about later on, you'll see it's labeled with a 1 up here, a hydrogen here, and a 1.0079 or something like that. So what this means is this right here, this is that atomic number. That's the number of protons. When you look at the charge on the nucleus for that hydrogen, remember that hydrogen has a 1H, 1.0079 is what it looks like. The charge on the nucleus is the same as your atomic number. Same as atomic number. The atomic number for carbon is 6. So it has to have 6 positive charges. It has 6 protons. So it's going to look like a carbon with a 6 here. And most of the time it's going to have 6 neutrons as well. Oxygen has 8 positive charges. So what's that going to look like? Here's oxygen with 8 protons, and its atomic weight is most often 16. So I used a term called atomic weight. So now then we have this right here, which is atomic, I'm going to call this not weight, but atomic mass. And I've got this thing here, which is your atomic number. Two different things. Atomic mass is protons plus neutrons. Notice I'm reminding you this right here. Protons plus neutrons. Atomic number is just number of protons, right? So, atomic mass. One of the interesting things here is this statement right there. Electrons are so small that they are neglected. In fact, electrons are approximately 1/1000th the mass of a proton. Electron is 1/1000th the mass of a proton. And we say that this mass of a proton is an AMU. AMU stands for atomic mass unit. So what is an atomic mass unit? It goes back to that mathematical tool. It is a little bitty mass of 1.67 times 10 to the negative 24th grams. Very, very small. And instead of trying to deal with 1.67 times 10 to the negative 24th, which is too tiny for my brain to wrap around, we say it's 1 AMU. So oxygen weighs 16 AMUs. Hydrogen weighs 1 AMU. Carbon weighs 12 AMUs. Elements represented by all sorts of things called symbols, and they come from lots of different places, lots of different reasons and whys that these things happen. Sodium originates from the Latin natrium, which means highly reactive, if I remember correctly. Potassium is calcium. Iron is ferrous or ferrum, which means magnetic. Copper is cuprous, which means bronze colored. Sulfur, we have all these different things that are represented by different types of symbols or atomic symbols. And when we put it all together, we get this thing called the periodic table of elements. And this thing is arranged in a very unique way that we'll talk about in another bit of the class. Each of these atoms are electrically neutral. That means you're always going to have the same number of protons as you do electrons. So an atom is electrically neutral. So if I put 12,6C, so I know that this carbon has 6 protons, right? So that also means it's got 6 electrons. Interesting. So 6 positive charges here plus 6 negative charges, if we add those things together, is equal to a 0 charge. So it's neutral. Atoms are always neutrally charged. But electrons can be lost or gained, just like money. So we can take sodium and we can lose an electron. So when we lose that electron, then that electron it flies off somewhere else. That means that sodium now has an extra proton. So we give that sodium a positive charge with an electron that popped off. Now, interestingly, you can take a chlorine and we can add an electron to it. And so now then we can get in Cl minus. So you can add electrons, you can subtract electrons. It's kind of interesting. On this periodic table of the elements on the left lose, look, elements on the left lose L and L, elements on the right gain. Okay? So when we're looking at the periodic table up here, this one is going to tend to lose 1 electron. In terms of the pattern, this is going to tend to lose 2 electrons. I'm going to skip all that middle stuff, and I'm going to come back over here. These are going to gain 1 electron. This one with oxygen is going to gain 2 electrons. So you start to see that there's a little bit of pattern. So if I have sodium bonded to chlorine, now then chlorine gains 1, sodium loses 1, and what happens is when you put these two things together right here, you get NaCl, also known as salt. So, where do these charges come from? It's just from losing stuff. Magnesium loses 2 things. It becomes the magnesium ion. So these, when an atom becomes charged, we call it an ion. Magnesium, when it loses 2 electrons, becomes a magnesium ion. When chlorine gains its 1 electron, it's called the chloride ion. So when you gain, I'm going to call this gainers, change names. And these gainers will then, in this case, chlorine, you drop the ene and you add ide. It becomes chloride. And so now then that chlorine, instead of having 17 protons and 17 electrons, now has 17 protons and 18 electrons. Notice that the difference here makes it a negative charge. So, with these periodic tables, you'll notice that the masses aren't whole numbers. So chlorine, for instance, is a 35.5 on the periodic table or so. So chlorine exists, mind you that there's a 17 there, as chlorine 35 and chlorine 37. So what this is saying, what happens here is that approximately, if I recall correctly, 70% of all chlorine in the universe is chlorine 35, and 30% of the chlorine is chlorine 37. Notice that these chlorines are still chlorines because they got the 17 protons, they got the 17 electrons, but they have different masses. When we take this and we weight it just like you would in getting a grade, that gives you a mass of 35.5. So if you take 0.7 times 35 plus 0.3 times 37, you know what you're going to get? It's going to equal 35.5. So, now then, these isotopes that we're talking about here have a specific isotopic ratio. That isotopic ratio lends self to this atomic, kind of a weighted atomic mass, or we call it atomic weight. Instead of calling it a weighted atomic mass, we get this thing called atomic weight. So it makes it a little bit simpler to think through. So again, we kind of see how this plays out in the next slide. These isotopes have the same number of protons but different numbers of neutrons. So, there's a crash course in atomic structure. Hopefully I didn't confuse you too much, but knowing these foundations will allow us to figure out how chemistry plays out in the long